Welcome everyone to this lecture on regularization. So what does it mean, regularization? Well, it's simply any strategy whose aim is to reduce test error, and especially when by manipulating the fit of the model to the training data and thus possibly increasing training error. And effective regularization is actually very important for deep learning as a major focus of research in deep learning. So regularization as a concept applies across machine learning, all sorts of different approaches, but it's especially relevant for deep learning because deep learning models are typically very large, very complex, typically have a lot of parameters. So regularizing them effectively is crucial for making them perform well on data which they haven't been trained on. So just a reminder of what we mean by model fit. So model fit is the degree to which the model captures the patterns in the data. And this is just an illustration of this concept in a kind of informal, intuitive way. So what we have here is two-dimensional data when there is just a few points, and we're fitting a curve to it, a curve defined by a polynomial formula. So a polynomial formula can range depending on its degree from linear to degree n. Polynomial, and the higher the polynomial, the more complex this curve can become. And so the shape of the curve depends on the coefficients, and these coefficients we fit to the data. And so what we have here on the leftmost panel is a linear model, which it is pretty obvious that it underfits the data, in the sense that it doesn't really capture anything much about these points. On the other hand, the rightmost panel is a complicated curve which goes like radically down and then sharply up, and it does fit the data in the sense that all the points lie on this curve. However, it seems to make some assumptions about the shape of the or the nature of the underlying process which is generating these points that are not really justified by what we see in the data itself. So it's overfitting. And finally, in the middle, we see something in between these two cases where the model is not too simple, not too complex, and it seems to capture the data but without making some extra assumptions. And so this is like an informal way of illustrating this concept, which you're already familiar with, but just as a reminder. So what we do with regularization is basically some way of manipulating the fit of the data, how much it fits the training data, and in what specific ways it fits the data, how it departs, and how it captures these patterns. With the aim of making it perform well on data which is not in the training set, so some other data. And so we will start with norm penalties. Norm penalties refer to constraints on the model weights or coefficients. So what we have here are is the definition of two penalties, L2 and L1, and these names come from the names of the corresponding norms. So L2 norm and L1 norm. And what we have here is our objective function J, which quantifies how much error we're making with the parameters W, with weights W, on the training data X and Y, where X are the inputs and Y are the labels. And then we have J hat with a little hat on top of the letter J. This is the objective function which incorporates the penalty. So it not only quantifies the error that we're making, with these weights W, but also it captures something about the complexity of these weights. And this notion of complexity here is very simple and straightforward. It's just a norm. So for L2 norm, that would be the sum of the squares of these weights, and for L1 norm, it would be the sum of the absolute values of these weights. And there is also this coefficient lambda, which controls how much this penalty is taken into account. Whether if we set this to 0, then basically this penalty is ignored. If we set to a large value, then this penalty would have a large effect, and the model will not fit the data very well, because it will try to make the norm very small, and so the weights won't be able to vary too much, and thus won't be able to fit the data very, very precisely. So basically, what we are doing with these norm penalties here is that preventing the model from making the weights too extreme, from varying too much, and thus from having the freedom to fit the data very well. And the two penalties have slightly different properties. So the L2 penalty simply shrinks the weights typically, so the weights become smaller, but not necessarily 0. Whereas the L1 penalty has the effect that some or many of the weights will become exactly 0, and so that will have the effect of actually ignoring these particular features. So it will have the effect of making the model sparse. The weight vector W here will be sparse in the sense that many of the dimensions will be 0, and so this can be seen as a form of feature selection. So let's have a look why that would be the case with the L1 penalty. And so what we have here, these concentric circles. This indicates the shape of the objective function in the weight space. So the darker the color, the lower the error is associated with a particular parameter, with a particular point. And each point in one of these plots corresponds to some combination of the two weights, θ1 and θ2. So we're talking about a model with just two weights here. And so on the left-hand side, we have the L1 norm. On the right-hand side, we have L2 norm. And these orange circle and the blue rectangle, the blue square, this corresponds to regions of this weight space which are within some particular norm, let's say the unit norm. So all the points within this region, orange or blue, are the norm of this weight vector is less than 1, if we assume that this is a region of unit norm. And so now, given that we want to stay within this region, we should find a point within this region which has the smallest error. And so if we do that, we will see that for the L2 norm, we just find some point with some particular non-zero weight θ1 and θ2. For the L1 norm, you will see that it will tend, as in this particular case, the point which has the lowest error, while at the same time being within this region, one of the weights is 0. So in this particular case, the θ1 is 0, θ2 has some other value. And so this is in general also going to happen in multidimensional weight space. So when we have not just two, but many more dimensions, that some of these will, because of the shape of this region of unit norm, that will be the case that many of the weights will tend to be 0 for L1 norm.